Hi everyone, myself Sadvik, roll number 20951A05G4, branch Computer Science Engineering, section C. The topic which I got for Tech Talk for the subject Design and Analysis of Algorithms is a class of sorting algorithms based on quicksort. First of all, introduction. Although there is no internal sorting algorithm that is best for every situation, the quicksort algorithm introduced by Hore is widely accepted as the most efficient internal sorting technique. Quicksort, quicksort sorts a list of keys A1, A2 up till AN recursively by choosing a key M in the list as a pivot key around which to rearrange the other keys in the list. Ideally, the pivot key is near the median key value in the list, so that it is preceding by about half of the keys and followed by other half. The keys of the list are now rearranged such that for some j, a1, a2 until aj contain all the keys with the values less than m and contain all the key values with values greater than or equal to tn. The elements a1, a2 until aj are called left sublist, and the elements aj1, j plus I1 until an are called the sublist, right sublist. Thus, the original list is partitioned into two sublists where all the keys of the left sublist precede all the keys of the right sublist. After partitioning, the original problem of sorting the entire list is now reduced to the problem of sorting the left and the right sublist independently. This is the algorithm or the procedure we follow in quicksort. There have been many improvements and modifications to quicksort, whereas quicksort partitions the original list using the first element as an estimation of a median. Quicksort partitions using the middle element list as an estimation of the median. Some additional decisions of quicksort may be found. And a more recent variation, mean sort, has been proposed by Motzing. Mean sort does not select any particular key to control and the partitioning process. Instead, the partitioning is determined by the mean value of each list. During the first pass, the first key is selected as the key controlling the partitioning process. While the keys are being compared and interchanged, the values of the keys of each subfile are summed. When the partitioning process is finished, the two means are computed. Each subfile from then on is partitioned based on its mean, and new mean values are computed at each partitioning step. For many distributions of keys, the mean value will be better estimate of the median value than a key selected at random. Furthermore, the distribution of the keys does not affect the performance of mean sort. Mean sort is one of the several algorithms that will be compared later in this PPT. This is the procedure for mean sort. However, the fundamental drawback of quicksort and its variation remains the same. The worst case behavior is big O of n square comparisons. Occurs when a list is nearly sorted or nearly sorted in reverse order. Although it would seem that a completely sorted or nearly sorted list would take the least time to sort, Cook and Kim have developed an excellent sorting algorithm for nearly sorted lists, which for lack of any other nomenclature we will refer to as CK sort. CK sort is a combination of straight insertion sort and quicker sort. The sort with merging and is designed specifically for nearly sorted lists. It performs poorly on any other distribution of keys, including nearly sorted in reverse order. In CK, in CK sort, the original list is first scanned. The pairs of unordered elements are removed and placed in an another array. After a pair of unordered elements has been removed, the next pair compared is the elements immediately preceding and immediately following the pair just removed. After repeating this for all elements in the original list, the array of unordered pairs of elements is sorted by straight insertion. If there are no more than 30 elements, and by quicksort, otherwise finally the two sorted arrays are merged into one array. B-sort. The technique presented in this PPT is a variation of quicksort that is designed to work best for nearly sorted lists as well as nearly sorted in reverse. For all distribution of keys within a file, bsort required no more than big O of n log n comparisons. In fact, for sorted lists or lists sorted in reverse, the algorithm takes big O of n comparisons. Bsort uses the technique associated with bubble sort. In a bubble sort, a check is made after each pass to determine if the list is sorted. If the list is sorted, the algorithm terminates and further passes are not necessarily, as the keys are being compared uh, and interchanged. It is easy to determine if the list is sorted or not after each pass has been completed. Similarly, after each pass in bsort, each subfile of keys is checked to see if it is sorted. If it is, the subfile need not to be partitioned again, while the keys are being compared and interchanged during the construction of each subfile. It is easy to determine if the subfile is in sorted order or not. It will be shown that bsort has no worst case behavior, that it works best for nearly sorted lists, and on an overall basis improves the average performance of quicksort. The algorithm for bsort. As in quicksort, bsort selects the middle key during each pass as the key controlling the partitioning process. The algorithm then proceeds as traditional quicksort. Each key that is placed into the left subfile is done so at the right end of the subfile. If the new key is not the first key of the subfile, a comparison is made between the new key and its left neighbor to ensure that the pair of keys is in sorted order. If not, then they are interchanged similarly. Each new key that is placed onto the right subfile is done so that the left end of the subfile, if the new key is not the first key of the subfile, a comparison is made between the new key and its right neighbor to ensure the pair of keys is in sorted order. If not, they are interchanged. Thus, at any point in the construction of the left subfile, the rightmost key will be the largest in value, and at any point in the construction of the right subfile, the leftmost key will be the smallest in value. When the partitioning process is finished and there were no interchanges performed during the construction of a subfile, then its keys are in sorted order and further partitioning is unneeded. The major advantage of bsort over quicksort, in addition, if a subfile has only two keys, then by the moment of construction, it is sorted. If a subfile has three keys, it can be sorted by making one comparison and possibly one interchange. A subfile will not be partitioned further unless it has at least four keys. Consider the following file with a middle key 35 as a pivot key controlling the partitioning process. We start with two pointers I and j pointing to the left and rightmost keys in the file respectively, that is 91 and 49. First we attempt to move I to the right and until a number larger than or equal to the pivot value is found. In this case, since I rests on the value 91, I does not change and remains on 91. Next, we move j to the left until a number less than the pivot value is found. This yields the following result. Exchanger keys pointed to by I and j. Now 91 and 49 are exchanged to preserve the property that the leftmost value in the right subfile is always the smallest value of that subfile. Since an exchange has occurred within the right subfile, the subfile will not necessarily be in sorted order with the partitioning process is completed. And the list is now shown like this. This yields the following list: 28, 62, 3, 84, 35, 10, 49, 97, 91. We exchange the keys pointed to by I and j, yielding this. We continue this process, and finally, the process terminates when I and j meet. The key pointed to by I and j must now be placed into the proper subfile. Since 84 is larger than the pivot, it belongs in the right subfile. 35 and are exchanged, yielding the final partition. One comparison and possibly one exchange. Thus, after exchanging 10 with 3, the left subfile is sorted. The original problem has now been reduced to sorting the file. Summary and conclusion. CK sort is still the best algorithm for nearly sorted lists. Although CK sort was not designed for the other than nearly sorted lists, we include performance on other data sets for the sake of completeness. Dash entries indicate a worst case situation where calculations were not made. Quicksort is still the best algorithm for random keys. In the worst case situation of nearly sorted lists or nearly sorted in reverse, the performance of quicksort is extremely poor. Mean sort proved to be the worst of the 7 algorithms tested with respect to CPU time, and BM sort was the worst by far among the class of B sort algorithms. Results show that both B sort and Y sort algorithms are considered improvements over quicksort, CK sort, and mean sort. B sort and Y sort have better average behavior in no worst case situations like quicksort and CK sort. Instead, they have a best case situation for nearly sorted lists or nearly sorted in reverse. B sort and Y sort are performed reasonably well on random keys and are particularly efficient in situations where they are repeating keys. With this, we have come to the end of the presentation. I would like to take leave from you. Thank you.